Good morning. Once again, welcome to A-Level Physics. Today's topic is on 1.3. Basically, we are dealing with errors and uncertainty. Before we go into the lesson, let us just review what we have learned from last week, from the previous lesson. Okay, previous lesson, we start for random errors. What is random error? Errors that cause the reading to scatter equally about a true value. There's a mean value. And when we take the measurement of diameter of the wire example, some will be higher, some will be smaller. So that's why it means why scatter equally about a true value. Example, measurement of length of wire. Right? We have to estimate the last significant figure. So there's uncertainty there. Estimate means uncertain already. Or diameter of wire, where you have to measure at different places and find the mean value. Room temperature, where it can change slightly. So we have to measure a few times at different times. Why? Error due to observer as need to estimate the last significant figure. Either it's scatter or we have to estimate the last significant figure. That's why we have random error. Some may estimate a bit too low, some may estimate a bit too high. It's all right. That's why we call uncertainty. Reduction or elimination, it can be reduced by taking more measurement of the quantities and find the mean. Right? That we call a sample. Or by plotting a graph and drawing a line of best fit. And we have started how to combine random error. Right? You have quantity A with its uncertainty, quantity B with uncertainty, sum or different. Right? The error in sum or error in different, error in this one, or uncertainty in sum, uncertainty in different. We just add this uncertainty, delta A plus delta B. Or multiply or divide, same thing. Right? Each of these will have its own proportional error. P will have delta P over P, Q will have delta Q over Q, A will have delta A over A, B will have delta B over B. We just add them up. No subtraction in error. Right? Or we times 100, we get percentage error. We add a percentage error. And then we have started this example. Right? Where quantity S is measured as 10 plus minus 0.2 cm. Then we try to get you to get familiar with it. What is delta S? Delta S is this one. Right? That is your S. That's your delta S. The proportional error is just this one divided by 10. Percentage error is just times 100. Okay, let's do a few examples, and then we can carry on with random error and systematic error. Right? And then we have our B. That's our S from the previous slide. That's our B and its value. So uncertainty in B. There's uncertainty in B. There's your B with its uncertainty. So percentage is delta B over B times 100. So 0.3 over 20 times 100, get 1.5%. Absolute error in X, we have to add your B plus S. Add these two together. Here we get delta S is 0.2. Delta B is 0.3. We get 0.5. So that's the absolute error in X. Percentage error. Okay, it's from our previous slide. Percentage error, we just take your, first of all, we have to add your X, find your X value. The x value is just your s plus b. So that's your s, that's your b. So we get 30. The percentage is 0.5. That's a 0.5 for delta s. Delta x divided by 30 times 100. 1.7%. Right? So that's what we have calculated before. So now we want to find there's your S, there's your B from the previous slide. What's the percentage error in delta P? Solution. Remember, we add the percentage error. Percentage in X, delta S, percentage in delta B. Minus 2 plus 1.5, is 3.5%. Let's try this question. There's a percentage error in C, percentage error in B, percentage error in A. These are the different quantities. And F, the formula A squared B cubed divided by C. Find the percentage error in F. So as before, right, we add the percentage error in A, percentage error in B, percentage error in C. But because of this power 2, we multiply by 2. Because of the power 3, we multiply by 3. There's no power here, so there's no multiplication. So we just add this one, put in the value. 2 times percentage error in A, 3%. 3 and percentage error in B, 2%. The error in C is 5%. So add them up, 17%. Okay. All right, let's try another question. If the speed of sound is found to be that is partial question, plus minus 3%, what should be the answer for the speed? Right? Usually if it's 3%, we don't have to worry about this one anymore. Remember that the uncertainty must be written to one significant figure. And the quantity that's the speed follow the uncertainty or the error. So that 3% is delta V over V times 100 plus 3%. In the value, round this off to 327 times 100 plus 3%. So we can calculate our delta V. Okay, so we get 9.8. So remember, it's one significant figure, so we write as 10. Right? In this case, the 0 is not significant. So it's only one significant figure. So how do we write the answer? Answer is 330 up to here. The 10th place, 330 plus minus 10. Or just make it mark clear right in scientific notation, 3.3 plus minus 0.1 bracket A times 10 to the power 2 meter per second. Then we can see this is one significant figure. This is one significant figure. Right? One decimal place. Both are one decimal place. The answer is dot B. Okay, let's go back to our photo. Carry on with our lesson today. Okay, sample. Right? Are we going to cover systematic error, effect of random error, and systematic error on graph, the term accuracy, precision, sample of measurement. Okay, so that's summarized for you. Right? Always refer to the syllabus, then we can know how wide we have to cover, and then do the partial question to know precisely whether we have interpreted the syllabus correctly. Right? What are systematic error? Example of systematic error, zero error, faulty measurement, faulty instrument, I give you wrong reading, constant time delay, stopwatch that has a value not set to zero, so it will constant delay. What's the effect? Constant error in all reading. It's constant, not like random error, right? Where it's scatter about the mean value. Why? Why do they have such error? Error in measuring instrument. Example, error faulty instrument. Right? Or the instrument didn't set to zero. Can be eliminated if you know what type of error it is. Example, zero error. To correct for the measurement, use the final reading minus initial reading. Or zero the instrument. Right? Example, this one has no zero error. It's exactly at zero. The pointer of the ammeter placed on the zero where no current flow through it. Zero error arises when the measuring instrument does not start from exactly zero. Error is of constant sign and magnitude. Zero error can be positive or negative. If it's here, it's positive. If it's below, it's negative. Right? So this one, no error. Pointer exactly at zero. This one has a zero error. Right? On the right of zero is positive. On the left of zero is negative. So negative zero error. So we have to estimate it's about minus 0.1. Right? The pointer of the ammeter does not place on zero. It's not at zero, but a negative value where no current flow through it. That's what it means by zero error. No current flow through it should be zero, but it's below. Like some instrument got a screw here for you to adjust it to zero. You can do that or you can correct for it. So in this case, the answer is estimated minus 0.1 ampere below zero. So all the reading, we have to add 0.1 to each of the reading. If we use the ammeter, this one is a positive zero error. The pointer of the ammeter does not place on zero, but a zero value where no current flow through it. No current flow through it has a positive value. So we have to estimate 0.1. So it means it will always give us a greater value when we use this instrument. So we have to subtract 0.1 from each reading. Right? For micrometer, there is no zero error. 0 and 0, they are in line. This one got zero error. Right? It's positive zero error. So we have to reading. All reading, we need to subtract 0.2. That's a 0.1, 0.2. That line coincide. Right? This one is negative. That's a 0. It's below there. So it's 1, 2, 3, 4. So the negative zero error. So it's, we have to add 0.04. Right? If we use this micrometer. Right? So it's just like a meter rule, where instead of you putting the rod at zero, you put it below zero. That's for this case. Parallax error. Right? We have to put our eye in line with the edge here. A parallax error is an error in reading an instrument and is caused when you are not lined up properly with the measuring device. Right? This one will read too low because she's reading here. Right? 18.2. This one will read too high because it's reading from here. 21.5. Systematic error. Right? Other example will be a slow stopwatch. Wrong assumption. Right? Where O level we use 10, right, for fast calculation, But in A level, we have to use 9.81. So we use 10, we are causing systematic error. We are giving the calculation always too high. Right? Or reading measuring cylinder. Right? That's where the right way to read. No parallax error. Or same as this one. Right? If we read this value, there's parallax error. So we have to read directly above the needle, this needle, and the image to inside. Parallax error is an error in reading an instrument due to the eye of the observer and pointer are not in line perpendicular to the plane of the scale. Right? So you have to put your eye so that that pointer hide this image. Okay, effect of random and systematic error on graph. A student measures the time for a ball to fall from rest to a vertical height h. Knowing that the equation is given you, h is half gt squared, applies, the student plots a graph, right? You plot a graph of this is your y, this is your x, that's your t squared. So this is your gradient. So effect of random error, right? Shown by points, sometimes above, sometimes below. So that is random error. It does not affect the slope. And the line we choose will be there are equal number of points above and below. So that's called the line of best fit. Right? That's a short form. So if our line is drawn here from experiment, then we have what we call systematic error, a constant time delay. Right? Instead of 0, there's a value already. There's a constant time delay. Right? It will shift the straight line to the right. Or we can see a sample of measurement. Right? We are going to accuracy and precision. Sometimes we may have to not only measure one value, but a number of values to estimate the value of G. Right? Student determine acceleration due to gravity. Okay, in O level, you will learn, or SPM, you will learn that this is accurate and precise. This accurate but not precise. Right? They are not near to the center here. This one is precise, they are close together, but they are far from the center. Or in this case, neither accurate nor precise. To be accurate, it must be at the center. To be precise, they must be close together. Right? Estimating random error. Normally, for diameter of wire, where the diameter is different at different position on the wire, we take several measurements of the wire at different position and find the average or mean diameter. By taking more readings, we reduce the random error. That is where you go to university. The more reading, the better. But for A level, you just need to take 2 or 3. Enough already. No need to take too many. Just to show you that you don't take one. If there's a sample, you have to take 2 or 3. Then we use this formula to calculate the largest value minus the smallest value and divide by 2. 3 readings are sufficient for A level. Right? This is the largest in the sample. This is the smallest value in the sample. Then we add. Right? This is a uncertainty due to reading the instrument, due to estimating the last figure. This is the uncertainty due to the instrument where you have to estimate the last value. This uncertainty because there's a scatter. Every time we read, the value are different from the mean value. Right? Example, G is 9.81. We want to introduce the term precision. Precision measures the closeness of a quantity in the sample. How close are all these values to each other? Right? They are not necessarily the same as this one. That's a true value. A micrometer is a precision instrument because it gives two decimal place. As it gave more significant figure, that is, it can read to 0.01 millimeter. Two decimal place is millimeter. So it's a precise instrument compared to a ruler. Precise means that the value are very close to each other. The readings are very close to each other, like this one. Very close to each other. So it's precise. Example, measuring of G by a student. The measurements are close to each other so that the measurement is precise to 0.1. Right? How do we get 0.1? The largest value minus the smallest value. So it's quite close to each other. Very close, 0.04. Largest, smallest, subtract. Then the other term is accuracy. Closeness of the measured value to the correct value. You want to know how close is the measured value to the correct value or the true value. So we compare the measured value to the correct value. Precision, we don't bother about the true value. Right? We are only worried, we are not concerned about the different values. So usually we calculate in terms of percentage, then we can see how close it is. It's very large, then inaccurate. It's very small, then it's accurate. Right? So we compare. Right? We want the positive value. Measure value minus true value divided by true value times 100%. Right? True value or correct value. For a sample of measured value is the mean value. Right? So usually the true value is the mean value. If it's a sample, small percentage or small difference in value means accurate. Or we can use normal distribution. Take a lot of readings and then draw the graph. And then that's the mean value. Right? That's the frequency. How many of them are with this true value? How many of them are in value below? Or how many of them are above the true value or the mean value? It's a bell shape. Normal distribution, the mean is mu. Mu is the mean value. What does the y value represent? Frequency or number with a particular value. Number of measurements and x-axis, quantity measured. Example, diameter of wire. The bell shape is narrow when the measurements are precise. So we say, if we see narrow, we say the measurements are precise. Or small random error. Either way, because it doesn't fluctuate that much. Accuracy and precision. In this case, this is a correct value or true value. This is a measured value. That's the mean value. Very narrow, so we say low systematic error. But the mean value and the true value, there's a large difference. Right? Difference between mean and true value. If it's accurate, low systematic error. Difference between mean and true value is very close. In this case, it's not accurate anymore. It's quite far away. True value, right? This is precise because narrow, the bell shape is narrow. Or we say small random error. Or precise, values are very close to each other. That's why it's narrow. Large systematic error in this case. Right? When we look at systematic error, we look at this is a true value. That's the mean value. They're very far away. Compare with the scatter between the mean value and any other value. So we can summarize it. Object measured, right? It can be length, it can be time, it can be mass. And then there's what you call a correct value. Carefully measured by scientists with the best available apparatus. Usually it's tabulated in handbook of physics and chemistry concern. Right? Example G. G is the standard value which has been measured accurately, 9.81 for a particular place. Measure value. So we have a correct value, we have a measure value. You are the one who measure it. So accuracy, we want to compare. Right? So we take the positive value, true value, correct value minus your measure value. And we convert to 100%. And the difference divided by correct value times 100%. Right? This one say we want positive, can be right? Whatever will have the one negative value. Right? You are the observer. And then the instrument you use. Object measure. Three things important. Object measure, you are the one who do the reading, and then the instrument use. Read wrongly. Right? Parallax error. Faulty instrument. Right? Instrument can be faulty. Example, slow stopwatch or zero error. Right? When we measure object, example, diameter of wire, it got different value. Value fluctuates about the mean value. Example, diameter of wire or background current. They count the radioactivity of the background. So we can differentiate it, random error and systematic error. All these are systematic error. All these are random error. You estimate too high or too low for particular length. You have to estimate the last value. Okay, let's try some example. Okay, in an experiment to determine the acceleration due to gravity, G, the period T and length of a simple pendulum are measured. The uncertainty in the measurement of length was estimated to be 4%, and that for the period T is 1%. The formula is given. What is the uncertainty in calculated value of G? I want to find the percentage uncertainty in G. Right? So in this case, it's multiply. Right? Percentage delta G, percentage error in L, percentage error in T because of the square there, we times 2. The constant 4 and pi square doesn't have, it's a constant. So it has no error. So it's 0. Put in your value. Right? Percentage error in L. Percentage error in L is 4%. And there's a 2 there. Percentage error in T is 1%. So calculate out 6%. So answer is donkey. Effect of random and systematic error. A student, this partial question. A student measures the time t for the ball to fall from rest to a vertical distance h, knowing the equation h equals to half gt squared applies. The student plots the graph. Which of the following is an explanation for the intercept on the t-axis? And the t-axis, that's a t-axis. Right? Let's look at the physics involved, which we will study later on in topic 2. Distance travel or the height h as the ball is dropped from the rest. Right? U equals 0, S equals to h, A equals to g, t, and then we take downwards as positive, we drop the ball. S equals to ut plus half at squared. Right? S equals to h, u equals 0, so that's 0. Half A is your g, and t squared. Or we can take square root of it. So we can either plot this graph to make it the straight line or this one. Right? So in this case, you use root h as your y, that's your x. So this is your gradient. Okay? So compare with the equation of straight line, y equals to mx. So to obtain a straight line, we plot h versus t squared, right? And the gradient is half g. Or we can plot this is your y, this is your x, so that's your gradient. That's your gradient. Right? What's the effect of air resistance? So we should get a straight line passing through the origin. Effect of air resistance. Okay? You drop to the same height. If there's air resistance, you oppose the motion, so the speed will decreases. For a short height, the effect of speed on speed is negligible. Right? It's almost the same. The air resistance the speed is very low, so air resistance is negligible. At higher height, the speed is higher, so air resistance is more significant. We will study this later on. For larger distance or height, the time taken will be longer and longer. So we should get a straight line that way. Right? Low speed, time is almost the same, but as the height goes further and further away, the time becomes more significant because air resistance becomes more significant. Constant time delay. Right? Instead of starting on time, you study a little time, a short while later. This will affect the time at each height. Time will increase by a constant amount. Every reading will have a constant amount added to it. Right? So this is systematic error. Effect of fast stopwatch. Right? A fast stopwatch gives longer time. Right? Instead of the correct reading, it gives a longer time, higher value. The time measured for larger and larger height would thus be greater and greater. For short time, the effect is negligible. Right? It's too fast, in short time, it's negligible. The effect will be like air resistant, something like that. Right? But it's a straight line. Right? Fast stopwatch, the error is always the same. So instead of reading for this particular height, there's a time. Right? It's faster, it gives a longer time. Accuracy means, what's the answer? B. Measurement is close to the true value. Right? Let's try this one. A fixed quantity x naught is measured many times in an experiment that has experimental uncertainty. So that is the true value. The graph is plotted to show the number n of times that a particular value is obtained. What does the graph represent? Right? That's your mean value. Compare the true value. So it's not accurate, but the bell shape is very narrow. The value are very close to each other. So it's precise, but not accurate. B. Let's look at 4 students, A, B, C, and D, carry out a series of determination of the acceleration of free fall. The table shows the result. Right? This acceleration due to gravity measured by 4 different students. Which result is accurate and precise? Remember, the true value is 9.81. Accurate, precise means close together. Accurate, you have to compare to the true value. Precise means that the value of G must be close to each other. Accurate means that the mean value of G must be close to 9.81. Right? So this one cannot be accurate. This one scattered too far away, so cannot be accurate. This one, the mean value is likely to be more than 10. Right? So it cannot be accurate. So this one looks like it's accurate, but it's also close to each other. Right? It's precise and accurate. A. Which result is accurate, which not accurate, but precise? It's close together to each other. So that's your B. Which has small random error and systematic error. No random error. They're very close to each other. And small systematic error compared to 9.81 is quite close. Which has a large random error and systematic error. Right? Random error, remember, you look at the value itself, they are very far from each other. Right? This one would be quite close to 9.81. So it is the systematic error for this one may be very small, but this one is far away. Right? You can take it around 11, the mean value, so it's very far away from 9.81. So it's large random error also. Largest is 12.6, the smallest is 10.4. So the answer is donkey. Okay, so let's solve one last problem. It's a partial question. 2016 June, paper 11. A calibration graph is produced for 40 emitter. Which emitter reading will be nearest to the true current? Right? Read every value. Right? True current. Right? And then this is the emitter reading. One. Right? This is 0.2, 0.4, 0.6, 0.8, and 0.0. So 0.2, this one is the same. Right? 0.2, 0.4, 0.6, 0.8. So 0.2, this one is about 0.2, 0.3 center there, 0.35. 0.4 is this one. This is 0.2, 0.4, 0.6. So 0.5 is here. So it's about 0.55. And 0.6 is here. This one is 2, 4, 6. 6 is about 0.6, 0.6 here, 0.7. And this is 0.8. This is also 0.8. So the answer is donkey. Okay, so that's the end of the lesson. Thank you. We end our lesson for today.